All right, let's try some of these proofs together here. So the process is we have to first prove that this sum formula will work for the S sub 1 case. So we use this idea to prove our S sub 1 case. And we say, all right, when we plug in 1, we should get the same thing on both sides of that equal sign. So if we simplify, and I'll use a little arrow here, we get 2 equals 1 times 2, so we get 2 equals 2. So we have proven that it works for the S sub 1 case. All right, now next up, I'm going to write S sub k and S sub k plus 1. So S sub k, we're going to assume that it works for the S sub k case. So we are going to say that assume this formula works. All right, so we're just replacing all of those n's with k's, and we're saying now assume that this is true. So I guess, and I always use an equal sign here, but you know what? I'm going to, instead of an equal sign, I'm going to use colon. All right, then we're going to prove that it works for the S sub k plus 1 case. So I've got to write that out, S sub k plus 1. So that means, again, we're going to take 2 plus 4 plus 6 plus 8 all the way up to 2k, and then we say, all right, now go to the next term, so make that 2 instead of k, make it k plus 1, equals, and then wherever we see k here, we're going to replace it with k plus 1. So I would have k plus 1 times k plus 1 plus 1. Now, my job is to show that this statement will be true, that the left side of this equal sign and the right side of this equal sign will simplify to be the same thing. The key to every inductive proof is this next piece. We assumed that this statement was true, okay? Which means that anywhere we see just the left side here, okay, so anywhere we see this 2 plus 4 plus 6 plus 8 all the way up to 2k, which I see right here, we can replace it with k times k plus 1 because we started out this entire proof with saying assume that that is true. So instead of 2 plus 4 plus 6 plus 8 all the way up to 2k, I'm going to write k times k plus 1. So now what I have to do is I have to continue writing what's on the right or the left side of this equation. So plus 2 times k plus 1 equals, and what we're trying to show is that this, when simplified, will be what we see here on the right-hand side. Now I'm just going to simplify that a little bit and make it k plus 2. All right, so there's a couple ways you can go about doing this. You could factor out, if you understand factoring by grouping. This right now is set up to do a beautiful factor by grouping. If you don't, your other option is to just simplify, right? So distribute this k. We would have k squared plus k. Distribute this k, and we have 2k plus 2. And then I just have to show that when I factor this, which, you know, before I factor, I should probably simplify it, right? So I'd have k squared plus 3k plus 2. Okay, and then if I factor the left side, I'm not going to go through the factoring process, but you're going to get k plus 1 times k plus 2. And what you've now shown is that the two sides are equal to each other. So that's the end of your proof. There's 3 steps, right? You have your first step, which is show that it works for the S sub 1 case. The second step is assume that it works for the S sub k case. And then the third step is now prove that it works for the S sub k plus 1 case. Okay, let's try the next 2. So the second one is just using your positive integers. And what it's showing, or what it's saying, is that when we add up all of the positive integers, 1 plus 2 plus 3, all the way up to n, this is a shortcut to actually find that sum. So just like in the last problem, I'm going to start by showing that it works for the S sub 1 case. So I'm really focused on from here to here when I'm doing that. And I'm going to plug in 1. So I plug in 1, and again, I'm going to go back to colon here. So I'm using this side, just that little chunk right there when I'm showing the S sub 1 case works. Plug in 1 for n, and make sure that that works. So I have 1 equals, so look, I'll have 1 times 2 divided by 2. There's a giant 1. I get 1 equals 1. So I've shown that it works for the S sub 1 case. Now, the next step is assume that it works. So assume that it's going to work for the S sub k case. So the S sub k case is just what we get when we rewrite the entire thing now, okay? So not just, from here on. We rewrite the entire thing. So we would have S sub k is going to be 1 plus 2 plus 3 plus 4 plus all the way up to n. And we have to assume then, I'm sorry, that would be k, not n. And what we're assuming is that that sum is going to be found by doing k times k plus 1 over 2. And again, that's just coming from what we have written up here. So I assume that it works for the S sub k case, and then my last step is to then prove that it will work for the S sub k plus 1 case. So prove S sub k plus 1. So the S sub k plus 1 case means take that same sum all the way up to k, but now go one more term. So make that k plus 1. Basically, take whatever you have written here and add 1 to it. All right, and then we've got on the right side of the equation, we're going to rewrite that so that each of these k's that we see here, we replace with k plus 1. Now, Mr. Middleman has said in the past what he likes to do even is go back up to this original form and rewrite it so that everywhere you see n, you replace it with k plus 1. Either approach will get you the same thing. We're going to have k plus 1 times k plus 1 and then plus 1 all over 2. Now what we have to show is that this works. This formula will simplify and the left side and the right side will end up being the same thing. And the key to this, like I said in the previous problem, is recognizing that you have this showing up right here. So because those two things are equivalent, we can say, hey, this can go in place of the 1 plus 2 plus 3 plus 4 all the way up to k. So I'm going to write that, k times k plus 1 all over 2. That's what this entire expression right here we are assuming will be. And then we just add on the rest, so plus k plus 1. And we want to show that when we simplify it, we're going to get what's on the right-hand side. And this is where your algebra comes into play. So I'm definitely going to make this a fraction, and I'm going to multiply so I can have a common denominator. So I'll multiply this fraction by 2 over 2. And then what I'll have is 1 fraction all over 2. And it's going to be k times k plus 1 plus 2 times k plus 1 equals, and what I'm trying to show that it is k plus 1 times k plus 2 all over 2. If you've already done the first problem and watched the video for the first problem, then you recognize this, right? This numerator is exactly what we had in the previous problem. Same exact thing. We just can distribute it, combine like terms, and factor, and we'll get this. If you haven't watched the first video, or if you have and you want to see another way to do this, we can talk about factoring out that k plus 1. So what I can do is I can recognize that this k plus 1 that we see here and here is a factor in both of these terms. Here's term 1, here's term 2. So what I can do is I can factor that k plus 1 out. Now, when I do that, what will be left after I factor out a k plus 1 from this term is just k. So I'll have times k. And then what would be left here when I factor out a k plus 1 is plus 2 all over 2. And look at that. The two sides are the same. And we have proven that that actually is a true statement. Okay, last but not least, we're going to take a look at the third one here. Now this time we're adding up all of the multiples of 3. So 3, 6, 9, 10, 12, 15, and so on, all the way up to whatever our n value is times 3. So just like we have in the previous two, we're going to show that it works for the S sub 1 case. Now remember, that just uses from here to here, and it plugs in 1. So I would say, okay, that's 3 times 1. Let me fix that again. Use a colon like I have been on the others. 3 times 1 equals, and then I plug in 1 into my formula. So 3 times 1 over 2 times 1 plus 1. And then I just have to show that those two sides are the same. So this is 3. I'm going to have 3 halves times 2, which there's a giant 1. So I get 3 equals 3. So what I've done is I've shown that it works for the S sub 1 case. Now I have to assume, that's my next step, so I assume that it will work for the S sub k case. So I assume S sub k, and that means I have to write that. So S sub k is going to be 3 plus 6 plus 9 plus ... all the way up to, instead of n, I'm going to write 3k. And that should be, instead of n, 3k over 2 times k plus 1. And now the final step. So those two are the prep work. The final step is really where all of the hard work is going to happen. We have to now show that this will work for the S sub k plus 1 case. So now's when the proof actually comes into play. So prove the S sub k plus 1 case. So I have to write that S sub k plus 1. Now we can go to what we've already written, all the way up to 3k. And then I just go one more. So I say now instead of 3 times k, I'm going to do 3 times k plus 1. And I have to show that that is equal to, now again, instead of k, I'm going to have k plus 1 plus 1. So I have to show that those two statements are equivalent. Okay, so just like in the previous videos, the whole key to this, I mean, if you can't get this part, this is what will trip you up, is that we know that this expression has something that it's equal to. So I find that expression right here, and I replace it with this. So I'm going to replace this expression with 3k over 2 times k plus 1. And then I have to continue on with what I have in my expression here. So plus 3 times k plus 1. And my goal is to show that that is going to simplify to be what I see on the right-hand side. Now, on the right-hand side, you know, there's a lot of ways that we can write this. I'm going to show you in the next step how I might rewrite it so it's a little bit easier to look at. But for right now, let's focus on the left. On the left side, remember my rule, and my students will know this, is that if I see one fraction in an expression, I make everything fractions. It just kind of gets everything so it's on the same playing field. What I recognize is that I have really one fraction here, one fraction here. I'm adding them together. I've got to have a common denominator. So my denominator, if I multiplied these together, would just be 2. I'm going to have to multiply this fraction by 2 over 2. So I will multiply, let me kind of squeeze that in here, by 2 over 2. All right, now what that allows me to do is create one big fraction, okay, all over 2. I take this first numerator, 3k times k plus 1. I'm just going to write it, 3k times k plus 1, plus, and then here I've got 2 times 3, which is 6, times k plus 1. So now I have to show, and I'm going to do the same thing over here, right? I'm going to put everything as one big fraction. So I've got 3 times k plus 1 times k plus 2 all over 2. Okay, so the next step here, let's go ahead and move up here, is to start simplifying. So on the left side, I'm going to go ahead and distribute everything I see here. Or if you wanted to, you could do like we did with the second problem and factor out a k plus 1. And you know what? That's actually quicker, but I'm going to do it the other way just because I'm sure most of you probably did this. So distribute the 3k. All right, so we're going to have 3k squared plus 3k plus, and then I distribute the 6, 6k plus 6 all over 2. Okay, and I want to show that that is going to be 3 times k plus 1 times k plus 2 all over 2. Now, here's the thing. In the numerator, first of all, let's combine like terms, right? So we'd have 3k squared plus 9k plus 6 all over 2. Again, we're trying to show that it's equal to what's on the right-hand side. Now, I notice a couple of things, right? I notice that these 3 terms all have a factor of 3, and I also notice that there's been a greatest common factor taken out. So I'm going to go ahead and take out that factor of 3. So now I have 3 times k squared plus 3k plus 2 all over 2 equals 3 times k plus 1 times k plus 2 all over 2. And then if you've done the previous 2 problems, hopefully you recognize that trinomial, because it does factor to just be k plus 1 times k plus 2, which thankfully that's what we were trying to get over here. Now, if you had recognized at this point that you could factor out that k plus 1, watch how much faster this problem goes. Okay, so let's factor that k plus 1 out. What I'm going to have left out of this term is 3k plus 6 here. And then I can take that expression, and in that second binomial, I recognize that there's a GCF of 3, so I can factor that out of everything, which would make that second binomial just 2. So it does move a little bit quicker that way. You can do it either way, though. Okay, nice work, guys. Hope this helps.